Hello guys, we're going to look at section 3.2, which is the derivative as a function. So if you recall, we said that f prime of x, okay, is equal to the limit as h approaches 0 of this difference quotient. So keep in mind that a function can be written as y is equal to f of x. And so this implies if I want to take the derivative, which is that f prime of x, which is what we're saying, we can write this as y prime. We can write this as y prime of x, or what we've already discussed, which this is f prime of x. And so remember, we say that a function is, I think we use this terminology, differentiable, okay, if f prime of x exists, okay? And so the process is called differentiation. So the process of taking the derivative, okay, is differentiation. Okay? If a function has a derivative, we say that the function is differentiable. So our first example, we want to prove that y is equal to x to the negative 2, which we can rewrite as 1 over x squared, is differentiable and calculate y prime. So to show that it is differentiable, we have to show that the derivative f prime of x exists. So in this case, since we have it as y, we're going to write this function as y prime for our derivative. Okay, and this would be equal to the limit as h approaches 0 of now that difference quotient. So in this case, it will be 1 over x plus h to be squared minus 1 over x squared all over h. Okay, so got to do a little bit of algebra here. So we notice that we have to get a common denominator of this numerator. So if I multiply this by x squared over x squared and this by x plus h to be squared over x plus h to be squared. Sorry, let me erase that. Then we get x squared minus x plus h to be squared all over x squared plus x plus h to be squared over h. I'm going to do like this. I'm not going to continue to write that limit, but until we take that limit, know that that limit is still there. Okay, so we have the limit. Okay, so let's do some algebra. Okay, so the limit of x squared minus, and I'm going to go and distribute, I'm going to expand this, and I get negative x squared minus 2xh minus h squared. That's distributing the negative once I multiply this through, and this is all over x squared times x plus h to be squared all over h. Okay, let's cancel out some common terms, okay? And keep in mind this is over 1, so if I multiply by the reciprocal, this h is going to move to the denominator. So I have negative 2xh minus h squared all over now this h multiplying by the reciprocal of x squared times x plus h to be squared. Okay? Now, what do I notice? There is an h in common in my numerator, so I can factor that h out, and I'll have h times negative 2x minus h all over h times x squared times x plus h to be squared. My h's cancel, and so now I'm going to write my limit back. I'm left with this here, 2x, excuse me, negative 2x minus h all over x squared times x plus h to be squared. Okay, so now plugging this in, now I can actually plug in my 0. So this is going to go to 0. This x plus h is going to go to 0. And so remember, this is x to be squared, so I have negative 2x over x to the 4th. Where'd that come from? X squared times x squared is x to the 4th. So simplifying, this is negative 2 over x cubed, or negative 2x to the negative 3. So since this exists, the derivative of this function is now this function here. For the next few examples, we're going to look at a couple examples of looking for the derivative. Okay, so in this problem, we're going to let f of x equal x. Okay, so if I take the limit as h approaches 0 of x plus h minus f of x, which is just x, okay, all over h, my x's cancel. I'm left with h over h, okay, which is the limit of a constant, which is a constant. So here is my derivative. Now we're going to look at this example here, where f of x is equal to x squared. So we find the limit as h approaches 0 of x plus h to be squared minus x squared. If we expand this, my x squares cancel. Okay, I notice that the terms I have left have an h in common, so I factor out this h. They cancel, and I'm left with the limit of 2x plus h. And plugging in my h, I get 2x, so this is my f prime of x when x is equal to x squared. So let's look at this last one, and this time we want f of x to be equal to x cubed. So we did x squared, x cubed. We're going to plug in the same, x plus h to be cubed minus x cubed over h. We take this limit. We'll multiply this through. We notice our x cubes will cancel. Okay, when our x cubes cancel, I notice that the three terms remaining all have a h in them, so I can factor out a h. In doing so, my h's cancel, and I have this limit here, and once I plug in my 0, I get f prime of x is equal to 3x squared. I challenge you to actually do these on your own to make sure you got the same values. So now we want to look at some new notation. So when we're talking about derivative, we say y prime, okay, or this f prime of x. Now we're going to add a new notation, which is our Leibniz notation. And what we can do is we can use this notation here, df over dx. This means I'm taking the derivative of the function f with respect to the variable x, okay? Or dy dx. And of course, since y is equal to f of x, this is the derivative of the function y with respect to x. Okay? So this is often seen. So for instance, the function we did before, y is equal to x squared on our last slide, okay, we have dy dx, now we can write as the 2x that we saw that we got. Okay? Or we can say that this is equal to y prime. Right? Or we can write this as d dx of the function y. What is the function y? It is x squared. So d dx of x squared is equal to 2x. Okay? And so these are some new notations. Now, if I have, say, df dx of my function with this line at 3, this means I'm taking the derivative of the function f with respect to x, but I want to now evaluate it at x is equal to 3. Okay? Sometimes this is dy dx where x is equal to 3, okay? But it means I'm evaluating my derivative with respect to x equals 3. So since it's 2x, I just say 2 times 3, okay? And I get 6. Now let's recall what this 6 means, because the 6 is the derivative. It is telling me this is the slope of the tangent line at x is equal to 3. So let's recall the derivatives we did. We said when f of x is equal to x, the derivative was 1. When f of x is equal to x squared, the derivative was x squared, and so on. And this is the first one we did. When x is equal to the negative 2, we have the derivative of negative 2x to the negative 3. This leads me to a theorem, and this theorem is going to be called the power rule. Okay? So the power rule says that for all exponents n, dx of x to the n, that means if I take the derivative of a power function, x to the n, it now becomes this new, because I might see a pattern here, and the pattern might be this nx to the n minus 1. This is going to be a very powerful rule, right? Because now if I have a function that is a power function, I can just use this function here. Okay? So for instance, let's look at this value here. My n is equal to 1, and so if I want to find f prime of x, this is x to the 1, I'll take n, which is 1, times x to the n, 1 minus 1, of course, which is x to the 0, sorry about that, which is 1. So we get there a little quicker than doing the full function. Here, my n is equal to 2. So f prime of x would be 2, our n, x to the 2 minus 1, which is 2x. N is equal to 3. F prime of x is equal to 3n, x to the 3 minus 1, which is 3x squared. Okay? N can be any real number, okay? Or in this case, it's negative 2. So I have f prime of x would be a negative 2, x to the negative, the n is negative 2 minus 1, which is negative 2x to the negative 3, which is what we have here. So now that we've actually done this, now we can use the power rule. Okay? And so the formal definition is to go through what we've been doing before. Now we can actually use the power rule if I have a power function. So now let's work a couple problems. Okay? Keep in mind, any real number will work. So it's valid for positive, negative, fractions, rational, irrational values for n. Okay, so n in this case is negative 5/3. So my n is negative 5/3 x to the negative 5/3 minus 1. And since it's a fraction, I'm going to write my 1 as 3/3. So I get negative 5/3 x to the negative 8/3. And we can leave it like this with a negative exponent. Okay. So this time my n is equal to the square root of 2, which is an irrational number. Okay, so it's still going to be n to x to the n minus 1. And we'll just leave it as this because we can't simplify this any. So what do we notice about this? This is d dx of 6. That's taking the derivative of the function y is equal to 6. Okay, so is this really a power function? Okay. It actually is. I can rewrite this as, of course, 6x to the 0. Okay. And so since that's the case, my 0, n is my 0, so I have 0 x to the negative 1, but it doesn't matter because 0 times any function is 0, which is going to lead me to a rule that the derivative of any constant is always 0. So the derivative of a constant is 0. So we have a theorem that says that f and g are differentiable. If they're differentiable, then their sum and difference, okay, are also going to be differentiable. And if I take the derivative of f plus g of x, the derivative of this function, it is the derivative of the sum or difference of each of these functions individually. Now we have our constant multiple rule that says if I have any constant c and that constant times the function is differentiable, and if I take the derivative of the constant times c, this is the derivative of that, it is just that constant times the derivative of that function. Now we're going to look at several examples using both of these principles. So let's look at this example. G of x is equal to 7x to the negative 3 plus x squared plus 5. So to take the derivative of this, we can write d dx of this function g of x. So it can be written in this form. Keep in mind, there's several different ways we can write this. Okay? And so now the sum and difference says I can take the derivative of each one of these pieces individually. So that's the derivative of this plus d dx, of 5. Okay? Now our constant multiple rule says it's just going to be 7, the constant, times the derivative of this function here. We can just rewrite these. When you guys get sophisticated, you will not write all of this out. And so after this example, I won't write it out anymore. Okay? But now I have as 7 times. Let's take the derivative. So my n is -3, x to the -3 minus 1, plus here my, oopsie, let me go back, plus my n is 2, x to the 2 minus 1, plus, what did we say the derivative of a constant is? It is just 0. So now I multiply 7 times -3 is -21, x to the -4 plus 2x. And so this is my g prime of x. So let's look at this example here. We want to find the points on the graph of this function here. F of t is equal to t cubed minus 12t plus 4, where the tangent line is horizontal. Okay, so what do we know about a tangent line? Well, what do we know about something being horizontal? What is horizontal? Okay, what is the slope of a horizontal line? The slope of a horizontal line is m is equal to 0. Okay, and what is the slope of a tangent line? That is just our derivative. So what are we asking? Where is the derivative equal to 0? So let's find that out. So f prime of t, let's use our, now without putting it together, we're going to do the derivative of each of these pieces. So I have 3 is my n, t to the 3 minus 1, minus 12 is my constant. I'll leave it there. Here my function is 1. My n is 1, so that's 1 times t to the 1 minus 1 plus the derivative of a constant again is 0. So what do I have? 3t squared minus 12, because this becomes t to the 0, which is 1. So f prime of t is equal to 3t squared. This is the derivative or the slope of the tangent line of my function f of x. Okay? But we want to know, where is this equal to 0? So let's see where it's equal to 0 by setting it equal to 0. We'll have what? 3t squared is equal to 12. So t squared is equal to 4. And so t is equal to plus or minus 2. So at f of 2, we got to find this value. Okay? And this is back into our original function. Right? Then it is what? We put in, we'll get -12. So this point is -2 comma 12. And then f of -2, we put it back into our original function, is 20. And then we get -2 comma 20. This is a rough sketch of my function f of t. So this is t and this is f of t. Okay, and so we know at this point here, what do we notice? We have a tangent line of 0. And at this +2 and -12, I also have a tangent line of 0. The tangent line to this point is 0. Okay, so this verifies that our values are correct. So guys, let's look at this function here. F of x is equal to the 4th root of x minus the cube root of x. Okay, so the question is, can I use the power rule? Okay, I have to recognize that I can rewrite this as x to the 1/4 minus x to the 1/3. And then if I can do that, I can use the power rule. Next, I want to actually evaluate this derivative at x is equal to 1. Okay, so we will write df dx, okay, would be equal to, here my n is 1/4, so I have 1/4 x to the 1/4 minus 1, which I'll write as 4/4. Okay, minus, and I think this is supposed to be a plus, so let's make this be a plus, and I think this is a plus, doesn't matter. Okay, plus, and so I'll have what? 1/3 is my n, x to the 1/3 minus 1, and so this is what? 1/4 x to the -3/4 plus 1/3 x to the -2/3. And so it asks us to evaluate this at 1. That means I am going to plug in 1 for my x's. And so I actually get what? 1/4, because 1 to any power is just 1, plus 1/3. getting like denominators, I'll have what, 3/12 plus 4/12, and so the value is 7/12. So this represents the slope of the tangent line at x is equal to 1 of my function f of x. Now we wanted to look at the derivative of the function e to the x. This is not a power function, okay? Because this is just, and this is an exponential function. The theorem says that if I take the derivative of e to the x, I just get e to the x. I will formally do this in class, the proof of this using the limit definition of the limit, okay? But using this, let's find the derivative of this function here. 7e to the x minus 12x squared. So the derivative of this function, the 7, so my constant multiple rule still holds, would just be 7. And the derivative of e to the x is e to the x. Okay? And then my constant multiple rule holds again, so it's 12. And then the derivative of x squared is what? 2. X to the 2 minus 1. So I get 7e to the x minus 24, x. So this is one of my favorite problems ever. Keep that in mind. The function is negative 7x to the e plus 2e to the x plus e squared. And we want to find the derivative of this function. So we'll start off. We know that negative 7 is a constant. But what is x to the e? Okay. This is x raised to a power. So this is just the power rule. This is not equal to e to the x. So the power rule says that I take my n, which is e. Keep in mind, e is just a number. It's not a constant. It's just a constant. It's not a variable. Okay, x to the e minus 1. Moving to my next term, my 2 is a constant, but now my x to the e to the x, is just the derivative of e to the x. So this remains e to the x. Okay? Plus, what is e squared? Okay? Is e squared this function here? Is e squared a power function? E squared is just the number 2.712 ... to be squared, which is just a constant. And what is the derivative of a constant? It is 0. So I got negative 7 e x to the e minus 1 plus 2 e to the x. And this is the derivative of this function.